Welcome to the 8th lecture of optical sensors course. In the last lecture we studied the basic phenomenon of total internal reflection and derived the expressions for the electric field and the penetration depth for evanescent waves which travel along the interface when you have total internal reflection. And we saw that there was a plane wave which had the amplitude decaying exponentially while it was traveling along it, the interface. In the present lecture, we will try to see how we can use this phenomenon for sensing applications, and if time permits, we will also see the basic characteristics of, say for example, absorption and dispersion of metals, and we will try to solve for the Drude model for conductors. So, till now we have been studying the dielectrics or insulators, and now slowly we will move into the metals and we will try to see metal optics. But before we do that, let us try to see what we have got in TIR. Also, if you remember that the penetration depth was lambda 0 upon 2 pi under root n1 square sin square theta 1 minus n2 square. If theta 1 is equal to sin theta 1 is equal to 1, sin theta 1 is equal to 1, d is equal to lambda 0 upon 2 pi under root n1 square minus n2 square. This is the minimum value of lambda d, that is the penetration depth, smallest value of penetration depth. This is smallest value of penetration depth. It was largest when we had theta is equal to theta c. If we have say lambda 0 is equal to about, let us give a value about 500 nanometers, and n1 is equal to say 1.5, n2 is equal to 1, then d is equal to d minimum is equal to 500 divided by 2 into 3.14 or pi, you can keep it pi, and under root 2.25 minus 1, which will roughly come equal to about 700 nanometer. So, you can see that this is of the order of the wavelength of light. So, it is very small, it can be hundreds of nanometers to few microns, but not more than that. So, it means that if you have a medium, the wave which is traveling along the interface, it can penetrate up to 700 nanometers, say for example. I think it will be smaller, say not 700, I think 70. 500 divided by this, it will be like 70 nanometers. So, it will be like hundreds of nanometers only. So, this is very small, it is not like penetrating more and more, but it can be up to few microns if we can design it suitably. So, this is such a small distance. So, there are other uses, say for example, fish vision. So, if you have a fish and if it sees the sky upwards, it will seem like it can see the sky, but if it sees at an angle say around 49 degrees, then it does not see the sky, it sees the bottom of the pond. So, it can see far away objects, but that at the pond, not at the sky. So, this is the problem with the fish. Okay. So, if you come at an angle which is larger, basically the fish cannot see you, right. And because of this total internal reflection only, the diamonds are so shiny, so bright. So, if you have a diamond and say if its refractive index is around 2.42, it has air which is surrounding it, then you have large brilliance. Now, if you put it in water, then it becomes less shiny. So, I am giving you a question, why, what happens to the brilliance when, why it is less shiny when it is in water. So, this is a homework for you. Now, we come to the basic question, can we do sensing using TIR? So, if you remember that sin theta c was equal to n2 by n1, right. So, it was n1 sin theta c was equal to n2. So, sin theta c is n2 by n1, that was we got. Let us say that we use a prism here, and Na is the refractive index of the analyte, Np is the refractive index of the prism, light is incident from the top, because of refraction it goes this way, it gets total internal reflected and you get the reflected light. You put a layer which specifically binds to the analyte. So, this all it says it has the refractive index Na. The field distribution I told you already that it is exponentially decaying here. So, you have this relation if you replace N1 and N2 by Na, Np and Na. Now, you take a derivative of this, you arrive to this, and then we have sensitivity. By this relation. So, I told you in the beginning of this lecture, in the first lecture, how we define sensitivity. Sensitivity was change in the parameter which we are measuring with respect to the change in the parameter which is being interrogated. So, here we are measuring, we are changing theta, and we are trying to measure it in terms of the refractive index. So, theta is being interrogated. So, that is why it is d theta c by dNA, and you arrive to this equation which is 1 by under root Np square minus Na square. What it means? It means that the sensitivity will be large. So, you will have S is equal to 1 upon under root Np square minus Na square. It means that if Np is greater than Na, much larger than Na, S is small. Sensor will have small sensitivity if Np minus Na is large. If the difference is small, Np minus Na is small, S is large. So, for high sensitivity of the sensor, one needs to have a small contrast between the prism and the analyte refractive index. So, let us take an example. So, we have a BK7 prism here, and we put water droplet here, light is incident from one end and it is gets reflected here, and we are changing the angle theta, and we try to measure the reflectivity of the p polarized light. This is my setup. So, the sensitivity is defined by this relation, and we come out to have a sensitivity about 79 degrees per RIU, that is refractive index unit, refractive index unit. So, one refractive index of change, this means that in change of refractive index 1, 79 degrees change happens in the theta critical. So, it has high sensitivity and sharp response curve. So, this is a very good sensor, this is a very sharp response, you can see around theta c. Okay. So, we are trying to measure this. If you change say Na, if you put Na is equal to say 1.33, now you added some sugar, so it became 1.35, what will happen? It can move, this curve will slightly move here. So, the position will change. So, want to measure the position of this. By measuring the change in position, you can say how much change in refractive index occurred. This is how you can use it for sensing applications. Now, that was one part. I mean, we used the critical angle for sensing, and that is beyond critical angle. There was the phenomenon of total internal reflection. But what happens to the evanescent waves? This is something which is basically interacting with the material of the refractive index of the analyte. That is what it depends on, and it is getting changed also because of that. So, the sensing is performed by the evanescent tail of the modal field in the cover medium. So, suppose I have an interface here and light is incident in this direction. What will happen, that you have a wave which has exponentially decaying amplitude and it moves along this interface. So, if you make a waveguide like I discussed, if you have two media having a refractive index slightly smaller than this. So, Ng is greater than Ns and Ng is also greater than Nc. So, what happens actually, that when light travels from here to here, you have an evanescent wave in both the cover and the substrate. So, the wave is travelling like this, the evanescent wave is also travelling like this, and the field is decaying exponentially in both the media. This is another example. If you have air and glass interface at certain angle, the reflected light, you get all the light reflected because of total internal reflection, and then there will be a wave which will be travelling along this interface. So, there are various configurations for evanescent wave sensing. One is grating coupled waveguide sensor. You have a waveguide where the coupling of light is done by gratings. So, here either you do by grating or you do by prism. Why we need a grating or prism? Because this is very small. The dimensions of the waveguide, the core of the waveguide is very small, and you want to couple light to this. So, the convenient method is either using prism. So, you have a prism from where light leaks out to the core, or you have a grating which basically sends all the excites many modes of this waveguide, and then you use it for sensing. In a planar waveguide sensor, you have this kind of arrangement where you have light incident at an angle, and you can measure it with the absorption or sensitivity with respect to this angle only. So, if you change the refractive index, say from Nc to Nc plus delta Nc, that is the refractive index of this cover, you can basically have the peak moving, and by measuring the change in this peak position in terms of alpha, you can say how much change in delta Nc occurred. That is how you use it for sensing. Then there are other configurations on plasmonic sensing. So, for example, there is something called guided wave resonance, guided wave, where you have a periodic structure with a varying refractive index. It is both dielectric, and then you have a waveguide and then substrate, and on top of this periodic structure you have analyte, and light is incident from the analyte side. So, what happens actually, that at the resonance, that the light certain wavelength gets guided into the waveguide. So, whatever gets guided does not come out of the substrate. So, you get either or it gets back and the guided mode couples back to the grating and then it gets reflected. So, you get a peak in the reflected spectrum or a dip in the transmitted spectrum. So, by measuring the change in this, the position of this dip or peak, you can say how much change in the refractive index occurred, or you use it for surface plasmon resonance sensors. We will discuss in detail this later. Here also you can see that this kind of waves which are evanescent in nature are excited at the interface of this metal and the analyte here. These are evanescent waves, and they sense the change in refractive index of this analyte. So, either you measure the change in lambda or measure the change in theta, and this is how you see that the change with the reflected light basically, and you measure by measuring the change in lambda and theta, you can say how much change in refractive index occurred. Then you combine these two, and then there are guided wave surface plasmon resonance sensors, where after the metal you put a dielectric layer which becomes a waveguide. Under suitable conditions, it can excite excite certain modes into the waveguide, and this can be used for sensing applications. Also, you have surface evanescent waves using photonic crystals or anisotropic films, and basically you can modulate these anisotropic films or photonic crystal structures, and you have deep and peak like structures, and then you use it the evanescent field for sensing. So, there are various configurations, and we will discuss few of them in detail, but I was discussing the penetration depth before we started seeing what are evanescent wave sensors. And I told you that for the example we had about 70 nanometer, we got the penetration depth. So, if you want to say suppose you have a penetration depth of say about 100 nanometer here for example, and you want to detect say a protein or virus or some bacterium as an analyte medium, what you see is this protein is all had overlap with the evanescent field. Virus has partial overlap and also the bacterium. So, this much portion of the bacterium it not seen by the evanescent field, while if you increase it the penetration depth say like this up to here maybe, then this will see all, it can detect protein, it can detect virus, it can see bacteria. So, you design the sensor in such a way that it detects a particular species. So, they both are useful. Suppose you want to detect protein, or at that sample also has bacteria and viruses, and you want to exclude them, you make the penetration depth small. So, it does not sense the bacteria at all, it senses the protein. If you want to detect bacteria, then this configuration with a small penetration depth will not work for it. So, one has to design the TIR sensor in such a way that the penetration depth is large, so that the evanescent field sees the whole cell, bacterial cell. So, this is called this penetration depth engineering, and this is important and it depends on the kind of analyte which we are going to sense. Let us try to understand analytically what happens to the evanescent field sensing. I mean, it is not just why it is important to have large volumes or something to have evanescent high sensitivity. So, how the sensitivity varies that we saw for critical angle, and what are other parameters which it depends on. To solve that, let us say that we have this configuration where you have a waveguide say that we call confinement region say NW, and this waveguide is fabricated on a substrate which has a refractive index Ns, and on top of the waveguide we have an analyte which has a refractive index Na. Because of the total internal reflection, we have evanescent field there, and this evanescent field covers a volume that is called the interaction volume inside the evanescent field region. So, the dielectric constant can be defined in these regions as this. Thus, when this is in the volume region of the waveguide, it is NVW square. If it is not in the volume region of the waveguide, then it is either Na square, that is the analyte, or Ns square. So, here it will be Ns square, or when you say epsilon. Now, let us see that what happens if I put a particle here. So, if I put a particle there, what happens that the dielectric constant or the refractive index of the analyte region will change slightly. So, let us say that it changes by delta epsilon. So, Np is the dielectric, do not confuse it with the prism refractive index, this is the refractive index of the particle. Okay. So, this is the refractive index of the particle. So, it will be Np square minus Na square, actually it will be like difference in the this region, otherwise it will be 0. So, when it is in the interaction region, there is a slight change in the refractive index. So, when there is a change in the refractive index, there will be change in the wave vector also, and let us say that Ki and Kf are the wave vectors, initial and final wave vectors, and Ei and Ef are the initial and final electric fields. So, Ki means wave vector before the particle was added. Particle was added, and Kf is after the particle was added. And same happens to the electric fields Ei and Ef. So, let us take first order perturbation approach. So, the wave equation we already know that the wave equation was del cross E, right. From there we got the wave equation. So, wave equation is like this, and after the particle is added, you will have this delta term like this. Now, we multiply this equation with E square, E star, Ei star, and integrate over the entire volume, and then subtract from 1 to 1. Say this is 1, this is 2. You apply this in 1 and 2, and you get to this relation. Okay. So, in the first order in delta k, you arrive to this equation, that small change in the delta k is this. So, the shift in the wave vector is equal to the overlap integral normalized by the mode energy integral sensing in the evanescent region. So, you can see that this is something which is called overlap integral. So, the more the overlap integral, the larger the overlap integral, the better will be the sensitivity, because the better will be the change in the delta k. So, the main parameter, so if I want to divide it by Ki, we arrive to this equation, where the field strength is given by gives the sensor geometry, nanostructures, localization, band gas and material parameters, and while the interaction volume in the evanescence region gives the, and the lateral depends on lateral propagation length and porosity also. So, if you have a sensor which has larger penetration depth, it will have larger sensitivity. So, if you have, so here is a something like you have two curves, and the sensor is suppose we are measuring RP, and we have two curves where this is one is lambda 1, this one is lambda 2, and you see that lambda 1 is smaller than lambda 2. That means I am talking about the evanescent wave sensor. So, you can see that at this lambda 2 the sensitivity will be larger. If you remember, I told you that penetration depth d was proportional to lambda. So, at lambda 2 the penetration depth will be larger, that means the sensitivity will be larger from here. So, it means that for red wavelengths, since the penetration depth is large, the interaction volume will be larger. I mean the electromagnetic field will interact more with the analyte medium, and that is why the sensitivity will be larger. While you have small sensitivity at blue wavelengths, where the penetration depth is small and the interaction volume is also small. So, this is something which is very important while designing a sensor. That is why when we have this evanescent wave sensors, now we try to move more and more towards the NIR region, because then the sensitivity becomes better. But then there are also other things which we need to take care of, and that is detection accuracy. What happens to detection accuracy and all that. So, when we move ahead, we will see that it is not just the sensitivity, it is also the detection accuracy which is important, and what happens to the detection accuracy at larger wavelengths. So, if it is also increasing, that overall performance of the sensor will not be affected, because the figure of merit was defined as the sensitivity upon delta FWHM. So, if FWHM is also large, then overall figure of merit of the sensor will not change. So, we will see these things, that what happens to the detection accuracy also. So, that was it for the TIR based sensors and evanescent wave sensors. In the next class, we will see the absorption and dispersion characteristics of conductors, and then we will try to solve for plasmonic sensors. Thank you.